talk about how waves inside a pipe can be set up. How do you get a standing wave in a pipe? And so a pipe's quite different to a string. In a string, it's the string itself that's vibrating, but in a pipe, it's the column of air inside the pipe that vibrates. And so we need to think about what that column of air is doing when we cause it to vibrate by doing something like blowing across the end of the pipe. That's how we do it. There's two different sorts of pipe. There's what we call open and closed pipes, and it's a little bit of a confusing naming system because the open pipe is one that has both ends open, whereas the closed pipe is one that has one end open and one end closed. It kind of makes sense when we think about it, because if both ends of the closed pipe were closed, we wouldn't be able to make that column of air inside vibrate. The weird thing about wave reflection at the open end of the pipe is that the reflected wave has the same orientation as the incident wave. It's just like reflecting a wave from a free end of a string. And so that means we're going to get constructive interference happening at the open end of a pipe, and that's going to cause an antinode. And so in our open pipe, if we've got an antinode, a displacement antinode, so the air particles are free to move backwards and forwards at the open end, if we've got a displacement antinode, we must have somewhere in the middle a node, and so our wave is going to look something like that. Our fundamental wave is going to look like that. With the closed pipe, it's partly the same. We've got an open end, and we know that there must be an antinode at the open end because those air particles are free to move. At the closed end, we've got a wall there, and that means that those particles, they're going to bang into that wall. They're not free to move, and so the reflected wave is going to be inverted, and we're going to get destructive interference at the closed end of a pipe. And so we're going to get a node there, and that means that we're going to get different waves occurring in these two different pipes. Look at this one. It looks like that. Now you might have noticed I talked about how we have a displacement antinode formed at each end of the open pipe. And that's because when we're talking about these waves in air, we also sometimes talk about pressure nodes and antinodes. And it turns out that whatever the particle displacement's doing, the pressure is doing the opposite. And so when the particles are moving backwards and forwards with maximum amplitude at the antinode, that's because they're open to atmospheric pressure, and it doesn't matter how many particles we push at there, we're not going to change the pressure of the atmosphere. And so this end of the pipe was always at atmospheric pressure, and this end of the pipe is always at atmospheric pressure. They both stay at constant pressure, so those are pressure nodes, whereas in the middle, the pressure can go up and down as those air particles compress together and expand apart, and so we get a pressure antinode. So pressure does the opposite from what displacement does. Normally we're talking about particle displacement. If we come across to the closed pipe, the open end is open to atmospheric pressure. It's always atmospheric pressure, whereas the closed end, because it's got a closed end, that pressure can go up and down because those particles have got a wall that they can build up against or spread out from, and so we get a pressure antinode.